Today's video lecture is to introduce second order differential equations, and the aim for today is to talk about what are these things, what are they used for, and what process do you go through to solve them. And this process is of course what we're really aiming to be able to do. I want to introduce it by way of looking at an example. So if we imagine a mat on a spring attached to the ceiling or something like that, and this spring is oscillating up and down in a liquid, and you can see the liquid inside here. So there's the mass on the spring inside some sort of liquid, which is the red color, and then we need to come up with a model to try and describe how this thing's behaving. So what are the forces acting on this spring or on this mass? Well, first of all, we've got the force due to the spring, which is given by Hooke's law, minus K, minus because of direction of the force, is a restoring force. K is the spring constant, and this force is proportional to X, where X is the extension of the spring, measured from some arbitrary zero. Another force acting on this spring is the damping force, effectively. As this mass oscillates up and down inside the liquid, there's some damping effect, and that damping effect is due to this viscosity of the liquid, which is given by this Greek symbol eta, which is here, multiplied by the velocity. So the force is a function of the velocity, and the force gets greater as it moves more quickly through the fluid. The more viscous the fluid, the greater the value for the viscosity E. And again, negative because it's a restoring force. It's acting against the gravitational force, which is acting downwards, which brings us on to the last force here, which is the what we use to the gravity acting on the mass. So the force is the mass times the acceleration due to gravity, A. Now, what we want to do is to think about what these three forces are in terms of the displacement x of the spring. So the first thing we need to do is to think about what does this part of the thing mean. d2x by dt squared, this should be. So what that's telling me is that the acceleration is the second differential of the displacement. If you think about velocity, velocity is the rate of change of displacement with time, dx by dt, and the acceleration is the rate of change of velocity. So that's dv by dt or d2x by dt squared. So we can write the force due to gravity as m d2x by dt squared. We've already got the force due to the spring in terms of this spring constant K, and in terms of x displacement. So that force is already in terms of the displacement x. The last one, the force due to the damping effect of in the liquid, that's related, as I said already, to the velocity, and as I've already said, the velocity is dx by dt. So how does that leave us? It leaves us with, at any instant, the gravitational force has got to be balanced by the force on the spring and the force in the liquid. So ma equals minus kx minus e to v, but as we've already said, a is d2x by dt squared, and minus kx equals minus kx minus e to dx by dt. If we bring everything over to the left-hand side of the equation, we end up with this, which is a second order homogeneous ordinary differential equation. It's an equation because there's an equal sign in it. It's a differential equation because it's got differentials in it, dx by dt. It's a second order differential equation because it's got d2x by dt squared, so the highest order of the differential is the squared, hence the second order. It's homogeneous because the right hand side is 0. And it's ordinary because it only involves the differential of one variable. There's only one variable that's changing here, and that's displacement x. And we'll exclusively be talking only about ordinary differential equations. Ordinary differential equations, or ODE for short. Now, that equation that we've just got here, this equation, can be solved, solving the second order ordinary differential equation. And if we look at the solution, here it is. And the first thing to strike you is that it looks as though this bears no relation whatsoever to the differential equation that was on the previous slide. It's got some sort of exponential function associated with it here. This is a minus exponential function, so that means that it's a decay function. And it's also got some sort of sine, trigonometric function associated with it. And if we look at the function that's being plotted, we can see that the function seems to have some sort of oscillation associated with it, and it dies away very quickly to zero. So it's got some sort of exponential decay combined with a trigonometric function. And this is a classic sort of example of the solution to a differential equation. At this point here, time is 0, and so this is describing what happens to the mass on the spring as time passes. We're not interested in anything happening to the left-hand side of the function over here, so when t equals negative, so the mathematical part of the function, we're only interested when it starts at t equals 0, and it looks at that point here, y, or x in this case, of displacement, equals 3. So up this axis we're plotting x, and along this axis we're plotting time, displacement against time. And we can see from it, it looks as though this mass is going to carry on going up from a displacement of 3 to a peak value, drop down to 0, and then go the other side of the function. Go the other side of the function. Here, around here somewhere. So it looks like there's a very slight amount of oscillation, but that very quickly dies away to nothing. This is a heavily damped or critically damped function, as we'll see. The key thing, though, is to talk about how do you arrive at that solution there, and that's what the next few sessions are going to be about. How do we get from a second order differential equation like this to the solution there? And also, how do you get from a model, whether it be a mechanical oscillation like this, or some sort of electric circuit involving capacitors and inductors, and from that those initial conditions, come up with a differential equation and then solve it. Notice that in any given situation we have some initial conditions. Initially, at time equals 0, what's happening to the spring at time equals 0? Y, the maximum displacement, is 3 meters, and the velocity is minus 7 meters per second. And so if we look at the graph on the next page, we can see that it's starting at 3, so the initial displacement when time equals 0 is 3, and there's a velocity of 3 meters per second, minus 7 meters per second. And we can see that it's actually got a velocity because there's a rate of change of velocity of x with time at that point. So certainly the velocity is not 0. Okay. So our overall aim is to solve non-homogeneous second order differential equations. Remember the one that we looked at on the previous couple of slides ago is homogeneous. In other words, the right hand side is 0. We're aiming at the end to solve non-homogeneous second order differential equations where you've got some sort of function on the right hand side that's driving the situation. So if we think of this model here, we would add some sort of driving mechanism that was forcing this spring to oscillate at a particular rate. So as I say here, non-homogeneous second-order differential equations are one where the right-hand side is not equal to 0. The general solution to equations of this form comes in two parts. So we've got the general form of a non-homogeneous differential equation is given by two parts. The complementary function is called, ycf for the complementary function, and the particular integral, yp. So we're going to end up having to come up with those two parts, and the overall general solution to the second order differential equation is made up of those two parts. The complementary function is a solution to the homogeneous form of the equation, in other words when the right hand side is 0. So we're going to focus on this part first. So we're just going to focus on finding the complementary function effectively. In other words, we're going to be solving second order differential equations where the right hand side is 0. And in this example that we looked at the start, that would be a free oscillation. In other words, we set the thing off, we extend it to a certain point above or below an arbitrary 0, this mass here, and then we let go and we let it start to oscillate. And there's a free oscillation. It might well be damped, as it is in this example, so the oscillation doesn't last for very long, but there's no driving mechanism to keep this thing oscillating. So we know that at some point, at some value for t, the oscillation is going to die away to 0. Okay, so we're going to concentrate on the solution to these homogeneous second order ordinary differential equations. Just think for a moment what that means. Homogeneous second order ordinary differential equation. Okay, how do we do it? Here are the steps that I'm hoping you're going to become familiar with over the next few weeks for solving a second order homogeneous ordinary differential equation. 3 steps to follow. 1, form the auxiliary quadratic equation. Come to that in a minute. 2, solve this auxiliary quadratic equation and then choose the correct form for the solution. And there are 3 forms that we're going to need to consider. So we'll look at an example of each. And then 3, given boundary conditions, initial conditions, find the values of the constants. Okay, let's have a look and see what that means. So, first of all, in step 2, it says solve and then choose the correct form for the solution. Well, this table of solutions are the 3 forms that we need to consider. We're going to be solving quadratic equations. So we'll get solutions or roots to this quadratic equation. And there are 3 different types of solutions we can get. The first type is if we get 2 real roots, 2 real solutions to this quadratic equation. And these are 2 different solutions. So we've got 2 values, k1 and k2. The second situation is where we have real solutions, but they're the same. So only 1 value, 1 solution, k. And the third type is if we don't get real solutions, we get negative roots, which means we've got to introduce this imaginary number j, and so we get 2 roots, alpha plus or minus beta j, where alpha and b, alpha corresponds to the real part of the number and beta corresponds to the value of the imaginary part of the number. And then we have on the right hand side of this table solutions. And what this is saying is if we have two real roots, then we've got an exponential solution where y equals some constant a, and then there's an exponential e to the k1, which is the first root, x, plus b e to the k2x. So that means we have two constants in this solution. And on the previous slide, as we saw, it says we need then to put in some initial conditions to find these values of the constants, so we can come up with a solution for the differential equation with the values of a and b calculated. So that's what we would do. We'd try in the first case, and we'll look at an example of that. The second solution, where the roots are the same, we notice that the solution has the form y equals brackets ax plus b. Again, a and b are these constants that we need to determine given some initial conditions. And now we've only got one root, so one exponential function involved with this with that root k in it. And then finally, we've got the complex roots. And here we have y equals e to the alpha x, which is where alpha is the real part of the solution. And then brackets a, so again we've got these two constants a and b, but now we've got some trigonometric function involved. The cosine term, cos of the beta x, where beta is the imaginary root, and sine beta x, where beta again is the imaginary root. And sometimes you've got both the cosine and the sine functions involved. Sometimes one of these functions, the cosine or the sine function, disappears. And if you think back to our original problem that we had with the free oscillating mass on the spring, which was back here, we've got an exponential function and a sine function. And so it has this form. So it looks like it might well be an example of the complex form solution to the auxiliary equation, where the cosine function has disappeared, or the cos of the function equals 1, so we've just got the a plus the b sine beta x, which gives us the form that we want in that solution. And we'll end up solving that one and seeing how that fits in, how we arrive at that solution, in other words. Okay, so those are the three solutions. So solving the second order homogeneous differential equation involves forming the auxiliary quadratic equation. That's actually very straightforward. 2, choosing the correct, solving that quadratic, and that just means using the quadratic formula or the perfect square method, or even factorizing, and then choosing the correct form for the solution out of that table we just looked at. And then, given some boundary conditions, find the values of the constants. So let's have a go at some examples. So example 1. We've got, okay, let's have a look at an example then. The first example that we're going to have a look at is here. 4d2y by dx squared plus 12dy by dx minus 8x equals 0. If you look at the original example we looked at with the mass on the spring, then the 4 could represent the mass on the spring, the viscosity of the liquid 12, and the spring constant k will be minus 8. So to solve this thing, this auxiliary, we need to form the auxiliary. And that just means, for reasons that you can look into if you're interested in one of the Helm booklets or a textbook, the differentials you're just replaced by the letter n. So the second differential is replaced by m squared, the first differential is replaced by m, and then if there is no differential you just put the number down. And so in other words, we turn it into a quadratic equation, and this is called the auxiliary. And there are very good mathematical reasons for why we can do that, along the lines of the fact that the solution to the second differential is of some sort of exponential form. We differentiate it once, we get an exponential, we differentiate it again, we just differentiate that exponential again. And because the exponential function is its own differential or its own integral, we can actually end up with this. So the argument is somewhere along those lines. But the bottom line is, as far as us engineers are concerned, is we just replace the d2y dx squared by m squared, dy by dx by m, and form this thing called the auxiliary equation. Now all we need to do is solve this quadratic equation and find the values for k1 and k2, the roots. So if I were doing this, the first thing I would do was actually try and simplify it and make the coefficient of m squared 1 by dividing through by 4. So I would get m squared plus 3m minus 2 equals 0, which makes the whole thing fairly straightforward. Sometimes these things factorize, sometimes they don't factorize. We can always solve these things using the quadratic formula, n equals minus b plus or minus. So it comes with talking and writing at the same time. The square root of b squared minus 4ac all over 2a. And if we focus on this for a minute, and look just at the root bit, the b squared minus the 4ac bit. B squared, 3 squared is 9, minus 4 times a times c. Well, c is minus 2, so you're going to get a minus to minus and minus is a plus. So we're going to get real roots, because we're going to get a positive number inside the root. We're still not sure quite yet whether or not we're going to get the roots equal, but we're going to get real roots. So we know we're going to get real solutions here. Anyway, let's have a look. So if we put in the values, so m equals minus b. b is 3, plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is minus 3, all over 2. So m equals minus 3 plus or minus the square root of 9 plus 4 3s are 12, 12 plus 9 is 21, all over 2. So carrying on, m equals minus 3 okay, go back a bit and edit from the start of the solution and then put these solutions in. So m equals 0.79 to two significant figures, or minus 3.79. So m equals 0.79 or minus 3.79. And now that gives us our values for K1 and K2. So K1 equals 0.79 and K2, our roots, minus 3.79. And these are the two roots, two real different roots. So we go back to our table, two real different roots. So the solution has the form y equals a e to the k1x plus b e to the k2x. So y equals a e to the 0.79 x plus b e to the minus 3.79 x. And we're not given in this particular example any initial conditions. We'll come to that later. If I'm being given some initial conditions, I would have been told, for example, when when x equals 0, y has some sort of value, and when x equals 0, the first differential dy by dx has some sort of value, and then you can calculate the values of a and b. But we'll come to that a bit later. So for now, we have that as our solution. And because we can't find the values of a and b, this is a general solution to the differential equation in this example. Y equals a e to the 0.79 plus b e to the minus 3.79x. If we can then go on and find the values of a and b, we come up with a particular solution for this situation. So that's the first example. Two real different roots. Let's look now at the second example. So, almost the same. 4d2y by dx squared plus 8dy dx plus 4 equals 0. So first job, to simplify things, divide through by 4. d2y by dx squared plus 2 dy by dx plus 1 equals 0. Now, form the auxiliary equation. Can you remember what to do and write that down? Try it. Hopefully you got m squared plus 2m plus 1 equals 0. Now, looking at this, I've picked this particular example. If you know a little bit about these quadratic equations, you might recognize this as a perfect square. To find out whether or not a quadratic equation is a perfect square or not, what I do is take the value of this, the coefficient of m, which is 2, half it, 1, square that, and if that gives me this number here, which it does in this case, then it's a perfect square. So I know this is the case of the second type, which is a perfect square, and a perfect square is one that has equal roots. So if you want to find out whether or not you're going to end up with an example with equal roots, you could just ask yourself the question, is this a perfect square? If I halve the coefficient of m, do I get the number that's on its own? If you do, it's a perfect square. So, carrying on, what does this mean if it's a perfect square? Let's move on and continue with the problem. And you might see that if you identify this as a perfect square, you can actually get to the solution much quicker. So, let's do what we did before. The quadratic formula, m equals, or k rather, is our roots, minus b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, a equals 1, b equals 2, and c equals 1. So let's put these numbers into the formula. So for our example, k equals minus b is 2, plus or minus the square root of b squared minus 4 times a times c, and c is 1, all over 2 times 1, which is 2. So if we move ahead with this, you might be able to see where I'm going. Minus 2 plus or minus, if we look at the square root now, we've got 4 minus 4 is nothing, and that's what makes it the perfect square over 2. So if we look at that, the answer is k equals minus 2 plus or minus 0, so that's minus 2 over 2 is minus 1, and that actually, we've got only one solution, and the solution is k equals minus 1. if we look back at this initial case for a second, and let's look at the perfect square idea and see how we can have got from this solution to the other solution much more quickly. So let's look back at the auxiliary equation. M squared plus 2m plus 1 equals 0. If I recognize that that's a perfect square, it means I can write this as m plus 1 all squared equals 0. Why is that? If we expand out m plus 1 squared, as an aside here, we get m plus 1 times m plus 1, which is m squared plus m plus another m is 2m plus 1. And if you look at that, you'll see that that is the same as that. So in other words, if you recognize this here as the perfect square, then that means you can rewrite it like that. Perfect squares can be rewritten like that. How do I know how to write this? It's the coefficient of m halved. Half of 2 is 1, so I write m plus 1 all squared. Here's another example. M squared plus 6m plus 9 is a perfect square. Why? Because half of 6 is 3 and 3 squared is 9. How can I rewrite this? M plus 3 all squared. And you might want to multiply out m plus 3 times m plus 3 and confirm you get what's above. So it's worth looking for the perfect square in these problems. The bottom line is, if I've got m plus 1 all squared equals 0, carrying on with this perfect square idea, then square rooting both sides, I get m plus 1 equals 0, because the square root of 0 is just 0, so m equals minus 1. And we get n equals minus 1, sorry, k equals minus 1. K equals minus 1, I'll root, because I'm using that, aren't I? And so, you see, same as in here. Same as in here, k equals minus 1. But much quicker. You should recognize that as the perfect square. So we've got one root, and it's k equals minus 1. So going back to our table, real roots the same. So what do we write? Y equals ax plus b e to the kx. So the solution for this has the form. So the solution for this example, y equals ax plus b e to the minus 1x, or e to the minus x. Looking at this again, ax plus b e to the kx. So, example 2, divide by 4, look for the perfect square. And in this case, I've hit jackpot, I have got a perfect square. So that means if I have recognized it, I can jump straight to this section here. If not, well, that's okay, I still get there, but I have to use this quadratic formula. Once I've got to the perfect square, I can very quickly find out what k is, minus 1, and then put it into the solution. Again, this is our solution, and I'm given no boundary or initial conditions, so I can't find the values of a and b, so this is a general solution. Okay, let's have a look at another example. Example 3. You won't be surprised to know that this is going to give us complex roots because it's the third example. I'd start off the same way though, divide both sides by 4, so I get d2y by dx squared plus 12 divided by 4 is 3 plus 20 divided by 4 is 5 equals 0. Okay, let's get this quadratic formula on the go again. So try not to mix up my symbols this time. I'm after my roots, k, well actually m equals, so we've got, what am I saying? First of all, I've got to find the auxiliary equation, haven't I? And so write down what the auxiliary equation is. Hopefully you'll get m squared plus 3m plus 5 equals 0. Quadratic equation, use the quadratic formula to solve it. M equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Plugging the numbers in from this auxiliary equation, m equals minus 3 plus or minus the square root of 3 squared minus 4 times a times 5 all over 2 times 1 is 2. Looking at this root, this square root, here we can see 3 squared is 9 minus 20. We're going to get a negative root, so we're into a complex solution. So m equals minus 3 plus or minus the square root of 9 minus 20 is minus 11 all over 2. So we've got a negative root. So what do we do with that? Remembering back to our complex numbers, m equals minus 3 plus or minus, I can split this root into the square root of 11 times the square root of minus 1. Gives me the square root of minus 11 over 2. The square root of minus 1 we can't do. That just makes no sense in the real world. So that's a signed letter J, you might remember. So m equals minus 3 plus or minus root 11j over 2. Now what I need to do is split this fraction into 2 parts. Minus 3 over 2 plus or minus square root of 11 over 2j. I've divided both terms on top of that fraction by 2. And now I can actually work out that m equals minus 3 over 2, which is minus 1.5, plus or minus, what's the square root of 11 divided by 2? 1.66. And if we look at this, this has the form of a complex root, alpha plus or minus beta j. So we can identify what is alpha, minus 1.5, and what is beta, 1.66. So those are the values that go into our solution. It's a complex solution. So let's go back to our table. Looking for the complex roots, y equals alpha x brackets a cos beta x plus b sine beta x. So let's write that form down. So the solution has the form y equals e to the alpha x a cos beta x plus b sine beta x. So putting our values in, for this particular case, y equals e to the minus 1.5x brackets a cos 1.66 x plus b sine 1.66 x. And that is a general solution because we're given no way of finding a and b. So this case is a general solution to the quadratic, to the ordinary differential equation. Okay, let's just have a look back at this again. So, the aim for today, ordinary differential equations. What are differential equations? They're equations because they've got an equal sign in them. They're differential because they've got differentials in them, dy by dx or d2y by dx squared, which makes it second order. What are they used for? They're used for modelling situations like this, masses on springs, and seeing what happens as the oscillation continues, and we can actually find a solution and plot how this mass will oscillate up and down. What process do we go through to solve them? Well, we've looked at the very first step of that, and that's to try and find the solution of the homogeneous form. Remember, homogeneous means the right-hand side is 0. What do we do to solve the homogeneous form of the equation? We form the auxiliary quadratic equation. So we replace d2y by dx squared with m squared, replace dy by dx with m, and then we put the constant in the equation in there to form a simple quadratic equation. We solve that quadratic equation, and depending on whether or not the roots are real and different, real and the same, or complex, we choose the correct form for the solution. All that leaves us to do now is part 3, which is given the boundary conditions, find the values of these constants a and b. But that's something we'll look at next time.